Hello students. Now today I am going to bring you a very interesting article in the form of a question, and the article is known as a sliding scissor. Now every one of us have a scissor in our household. You can grab one with you like this, and then you can have a ball in your household like this. So that's a ball. And what do? We try to grip this ball with the scissor. So we try to grip this ball with the scissors. So what happens? There is supposed to be a particular angle at which it is going to be in a state of equilibrium. That is at a particular angle itself. If you try to increase or decrease the angle, it will not be in a state of equilibrium and it likes to slide. It likes to slide, right? And now instead of this, you can have a wire. You can have a long wire, and that particular long wire is supposed to be gripped by this. So let me show you a long wire. You will be wondering where is Servon. So there is a wire, and this wire is supposed to be gripped like this. Grip like this. Somewhere like this. In this mannerism, it should be gripped like this. Okay, like this. Let me hold it from here. Like this, it is to be gripped. Okay, so now it becomes gripped like this. Now see this section over here is getting gripped like this. So there is tiny angle over here. There is a very tiny angle. If I take a very thick kind of a wire, and this is just a wire, I can take this pen, a very thick kind of a pen like this, to hold the C slides, and then it becomes stationary. Right? If I hold it here, it slides. Are you able to see? Right? And then it becomes stationary. So little activity makes us understand that there will be a perfect angle at which it is going to remain stationary. The minimum angle at which it is going to remain stationary. See this. Right? So the question is based upon this idea. Oh, my pen got a little scratch because of this, because of the activity. So let you bring upon a question and solve this. So that's our sliding scissor. Let's read the question carefully. It says there is a pair of scissors used to cut a wire of circular cross section. I did not cut the wire because that was an expensive cable. You can cut the wire at your home. And it was held vertically. To reduce the required force, the wire must be placed close to the hinge. So we are saving our force. It should be placed close to the hinge. So where is the hinge, my friends? So that's the hinge. It is supposed to be placed close to this hinge. Now why you are drawing a circle? Well, actually it is supposed to be a wire. Like a wire. But then we are holding this like this. So if you see from the top view, you will see a circular section. So we are inviting a top view from here. And then we are observing this as a diagram. It slides away from the hinge, until the angle between the blades become theta. Let's observe that. So this is like this. I have just started folding this such that this particular angle decreases. So imagine that this was a diameter of the wire. So now if you bring these together, so this size will not fit here. So hence it is going to slide and it reaches this position. Whatever the size is going to be there. Now at some angle, and this is the angle of the hinge over there, and that angle is supposed to be given as theta. So find the friction coefficient between the blades and the wire. So the question isn't difficult. It's not difficult. So let's solve if it is not difficult. And what's the question concept? Let's first of all sketch. So just imagine that this is a equilibrium position. Oh, you are not able to see the scissor? So this is like a scissor. Okay, and then we have a ball or a wire. From the top it looks the same, which is gripped here. So that is gripped here like this. While the central angle over here, this angle, this complete angle is theta. So these half angles will be theta by 2. This one and this one. and this is our hinge over here, right? So that's the making of the diagram, and that's quite simple. What's the concept? The concept is too simple. The concept is supposed to be to first of all construct the free body diagram, and then after that just check in the condition of the equilibrium, and you are through with the questionnaire. So not so difficult. See, it wants to slide this side, this way. So there must be some forces which are acting in that direction. And that is acting because of the contact of this with the blades, which generates a normal reaction perpendicular to this. So that's the normal reaction, and that's the normal reaction passing to the center of this. And there must be a component of this over here, of this normal reaction. Which component? This angle is theta by 2. So this angle will be theta by 2. So the component of this n must act in this direction. Which one? That is n sine of theta by 2. Similar, a component of this n also acts in this direction by symmetry over here. And now you can feel it. Now you can feel it that these two forces are going to push this wire outward, push it outward. But then who is the savior? The savior is supposed to be the friction, which hates slipping, which hates slipping. So where is the slipping? The slipping is here. The contact point shifts. This is a contact point and this is a contact point. So the slipping is here. That's the direction of the slipping. That's a tangential slipping. This is how it is going to slip. While you are observing that it's moving here. So therefore the friction, who of course hates our slipping, is going to act in the opposite direction. So that's how the friction is going to act. It's opposite to the slipping. And then there is a component of this friction. If this angle is theta by 2, alternate angle, so the component of this friction acts here as f cos theta by 2. Similar here, over here, this angle theta by 2, so this angle will be theta by 2, and the component of the friction acts here as f cos theta by 2 here. And now there is a complete feel of the question. These two forces here are balanced by these two forces. And hence this wire can stay in the state of equilibrium. Right? So balance it, balance it. So we have twice of n sine of theta by 2 is equal to twice of f cos of theta by 2. Like this. And what's the friction force? The friction force is supposed to be mu into n. We know that. That's the sliding friction. So it almost solves the problem. That's n sine theta by 2 is equal to mu n cos of theta by 2, where the n gets cancelled out, and sine theta by 2 by cos theta by 2, that becomes tan of theta by 2, and that becomes equal to mu. Is equal to mu. So does it fit the options? I bet it. This can be written as mu as equal to tan of 0.5 of theta. And that beautifully fits the B option. So the question was solved. The question was solved and not with much of a difficulty. The question could be increased in the level while basically gripping this, we can also accelerate the frame. We can also move the scissor forward. We are in a hurry and we are running. So you can accelerate it. If we accelerate our hand, stay stationary, accelerate the hand. So this becomes a what? A non-inertial frame. And so that ball is going to experience what? A pseudo? Yes or no? Think about it. Pseudo fascinates us now. So I brought another one with us. Now the question is regarding a prism and a bar. There's a prism and there is a bar. And a bar is kept on a prism. You can also say a block is kept on a wedge, right? But the erudite language says that exactly that's a prism and that's a bar. Okay? And what does a bar does? The bar is going to slide until unless there is a friction. So in this question, the question is telling there is a friction. And even because of it, what happens? This is sliding. Maybe. The conditions are supposed to be checked upon. And then it says this prism is given a horizontal acceleration towards the left. Check the reading. It says it gets a horizontal acceleration to the left, towards the left. And so we need to find a maximum value for the acceleration such that a bar, this block, remains stationary with respect to the prism. Now, this reminds me of a basic question, that means much basic than this. And what's that particular question? That we have a prism like this and a block kept on it, and this block is not allowed to move relative to this. It can move but not relative to this, for which we have applied a force in this direction, and this plane is smooth for now. So that's a degraded question in comparison to this. I will be back in 5. My camcorder would have got discharged, right? So the case is that this should remain in a state of rest with respect to this. Now that's a very basic question, and how do we solve it? And why is this force applied? There are very few concepts behind the solving of the question, where the concept 1 states to create an FBD and then check the scenario. So we started constructing the free body, and we got, if the mass of this is m, there is a force mg sine theta acting on it, which is basically responsible for sliding it downwards. And since there is no friction, so it must come down. So we generated another force via an acceleration. What happens via an acceleration? The acceleration received by this wedge or the prism, let's say, is A, due to the application of the force. It gives us a status as a non-inertial frame. And as it becomes a non-inertial frame, it has all the rights to apply a pseudo force on this block, because now we are solving from this frame and not from the ground frame. We are talking in a language that this block was sliding relative to this plane, where this plane was having an acceleration A. So we are observing an observer on this plane. And what does he observe? He observes a pseudo force, a fictitious force acting on this block in the backward direction, opposite to the frame acceleration. Assuming this particular angle is theta, so this angle is also theta, of course, and by corresponding angles. So there is a component of it, that is ma cos theta, which can balance mg sin theta. And so this question is getting completed by the application of the pseudo, that is a non-inertial frame, and observing this particular question from the frame of view of this plane and not from the ground. It becomes easier to understand. And so the pseudo start becoming our friend. In the previous articles also, the pseudo works as our friend here also, to solve the question effectively, easily. Of course, Newton might get a little bit objecting to this, but pseudo has become our friend. And the third concept, is there any third concept? There is. That might not look like to you as a concept, but it is. You study this as a separate article, and that's equilibrium. And that's what it is. It is in a state of equilibrium in this direction. And hence it is not moving in this direction. And that's also a question. That the net force is getting balanced. So you have ma cos theta that balances your mg sin theta, where m gets cancelled. So the acceleration that becomes g tan theta. And this is the kind of a question which you would have done. is slightly more than a basic level and less than an advanced level. What is the force which is required to basically produce this idea? Let's say this mass is capital M and this is small m, and now they become a unit. Reason because this is stationary with respect to this frame. It's like you are sitting inside a car. So what is the net mass of the car? The car mass plus your mass. So what is the net mass over here? That's capital M plus small m. And they are moving with an acceleration in. Because of what? Because of the force on it. And so we are able to get the value for the force as capital M plus small m into g tan theta. And you also get a bonus question. You also get a bonus question regarding what is a reaction force. And see, there isn't any friction. So the reaction force is entirely the normal contact force. So what is the normal contact force? That's equal to mg cos theta and plus something else. Of course, you don't forget that. Reaching to the levels of the JEE Advanced and Olympiad, we don't think that we are gonna lose the component, lose the plot. So the second component of it, that is MA, acts here. And what's that component? That is MA sin theta. They together generate a compression which creates a normal. So the value for this normal reaction is equal to mg cos theta and plus MA sin theta. Looks like a long term. We can reduce it by placing the value for A as g tan theta, that is g sin theta upon cos theta, and into the sin theta, so it becomes sin square theta. So it reduces just like this. That's cos square theta plus sin square theta in the numerator and upon cos theta. So the numerator becomes 1 and the result becomes mg upon cos theta, which you can also left to right as mg secant theta. And that's a complete solving which the question could have demanded over here from the non-inertial frame. Now see, would you like to ask me a question, sir, can we solve this question from an inertial frame? See, this is a longer version, the normal reaction to be calculated, and I will be solving for you the normal reaction from the ground frame. But that understanding is facilitated after understanding this. So this is a beautiful idea what we have learned. And now, as a bonus learning, now we have got to learn that this is not sliding on this hair. But that does not mean that it is in a state of absolute rest. It is in a state of relative rest with respect to the prism, but it is still moving. You are inside a car and you are still moving because the car is moving, which means that the absolute motion of this is in this direction. That is acceleration in this direction, and that acceleration is also for this block. For this block also. This is just not for this prism, it's for this block also. Now, as the force is acting here, there is no denial that the force is acting here, but there is no force in this direction. As I am walking here, watch my walk, not much prettier. As I walk, so definitely there is a force in this direction, but in this direction, vertical direction, there ain't any force. Similar to if you are driving a car on a straight road, a horizontal road, so there is a net force while you are accelerating in a horizontal direction, but vertically your car is balanced. In this direction also your car will be balanced. Only in this direction you have a force. So the concept can be really interesting to say that in a direction perpendicular to the net motion, this is a resultant motion, and in a direction perpendicular to this, we should have a balancing act. So let's balance the force in this direction. mg on the block is acting vertically down. So there must be a component of some force, and that's only normal. Only normal, because there is no pseudo now, because we are analyzing from the ground frame. So the only concept left is supposed to be what? The free body, that's all. But the second concept has arisen. And what is that? That is, the forces should be balanced in a direction perpendicular to resultant motion. We know that. the perpendicular forces cannot perform the work. And therefore, they must have balance with each other in some form. Over here, in this condition. Because there isn't any change in the direction also. Otherwise, it would have been a centripetal also. So the component here, can you check the angles? Of course, this angle theta, this angle theta. So this angle theta, the component becomes how much? N cos theta. And then in this direction, that n cos theta becomes equal to mg. So the value for the n becomes equal to mg upon cos theta. So the solution comes real quick and of course matches with this idea. So the explanation was more time consuming. The solution is like that. So it's done. And sir, you might be asking to me, sir, can you please explain to me what happened to the second component of it? That was n sine theta, which was responsible for this acceleration. Because of this particular component, this block will be moving. See, why is this prism moving? Because of the applied force. And why is this block moving? That is because of the acceleration. So that is n sine theta as equal to ma. So can we write that? Of course, that will be n sine theta as equal to ma. So you get two equations. You get two equations. And can you solve it from there? I think you can. I think you can. When we on dividing this, we are getting sin theta by cos theta tan theta equal to a by g. And you get the solution. This is without friction. This is without friction. And now enters the friction in this scenario. And the language. And the language is at what maximum value of the acceleration will the bar be still stationary. When this language arises, so we have to be careful while justifying the direction of the friction. So that will be an additional concept to the question. The previous concepts remaining the same, that is the concept number 1 will be to construct the free body. The concept number 2 will be to check the non-inertial frame, and that means the existence of the pseudo over there. And the third concept is going to be once again to establish the equilibrium, and where you can falter can be the concept number 4, that is to justify the direction of friction. So if you just cater to these things in a proper mannerism, the question will not be a sore for us. It will be a simpler approach to us. So let's keep in mind all these things and construct the free body. So what are the forces? There is a normal reaction. There is mg cos theta. There is mg sin theta, which will like this block to slide down. And why? We have done something for it. We have provided it an acceleration w. I am writing w as equal to a here, correct? At the last step, I can substitute w as a or a as w, right? And that is in this direction. Which direction? That is in this direction. Left forward. It says that. The horizontal acceleration directed to the left. So what happens? This gets a status of non-inertial frame. The prism gets a status of the non-inertial frame. And so we are solving the question from the frame itself. And solving the question from the frame itself, we get a pseudo in this direction opposite to the acceleration, to that additional force. And now we take a component of this as we did in the previous question. This angle is given alpha, so just leverage this angle alpha. So the component of this becomes ma cos alpha, and the second one over here, that becomes ma sine of alpha. So whatever we did in the previous question, we have already completed here. Now comes what? Additional language. And what is that? At what? Maximum. At what? Maximum value of the acceleration. What do you learn from it? Where is the friction? I don't know. You know, because the question says that. Justify it. How come? See, if the A is more, ma cos alpha will be more. And it might be more than mg sin alpha. And in that condition, this has a tendency to slide up. See, it is not sliding at all. So such questions are of impending motion state. So this justifying the direction of friction is basically an idea of what? The impending motion. And in that impending state, the friction directions changes. Like what? Like suppose the acceleration was a lesser acceleration, then the pseudo force will be lesser. The component will be lesser. Ma cos alpha will be lesser in comparison with the mg sin alpha. It has a tendency to slide down. So the friction has a tendency to act up to oppose the slipping. But that's not the case right now. Right now the question is telling us that the A is maximum. So I have to consider A to be maximum. So this is maximum. So the tendency to slide is upward, right? It has a tendency to slide upward, and as a result our dear friction friend is going to act tangentially downward, thus opposing the tendency of the sliding tangentially upward. And now see, everything is not moving, everything is stationary because everything is in a state of equilibrium. So balance up, and your question solving is just around the corner. So there is a pretty feel in solving the questions which I have solved for you. At any moment of time, we did not find that a question is out of reach. And that should be the kind of preparation strategy, that questions are in our reach via analyzing multi-concepts. Balance along this direction. So we have mg sin alpha plus friction as equal to ma cos alpha, correct? The coefficient of friction, the friction coefficient is given as k less than quad alpha. And what does that mean? K less than quad alpha. What does that mean? What this sense has? I don't know. We have to check that. K is a friction coefficient. We say it to be mu. The Erodov says it to be k. Of course, that's an Erodov question. 1.80. Well, how do we write a friction? Friction is equal to mu into n. How do we write a value for n? We have checked that. N is equal to mg cos theta plus ma sin alpha. So mg cos theta plus ma sin alpha. You place this n here and then you place this friction here. So not much of a problem. So mg sin theta plus friction, which is mu into n, and n is from here. That's mg cos theta and plus ma sin alpha. This all together balances ma cos alpha. So that's equal to ma cos alpha. Now what do we wish to find? A max. This is all A max. This is what we wish to find. That is a maximum acceleration. It appears twice here and here. So combine the terms. And this m gets cancelled. Oh, we never realized that the masses were not given. So it would have been an extra info, but not required in the question. So not given. But that g into sine of theta plus mu cos theta is equal to over here. That's A max cos of theta minus from here mu sine alpha. So I think we have got the result that the value for the A max is equal to g into sine of theta and plus mu cos of theta and divided by cos of theta minus mu sine of alpha. That should be your answer. And tata bye bye. No. Reduce it. So why? Just do it once. How come? Let's divide this whole idea by let's say sine theta, the numerator and the denominator. Okay, so that should be g into 1 plus mu cos theta by sine theta cot theta. It was all alpha basically. It was all alpha. All alpha. There is no theta anywhere. This is all alpha. This is like every theta always remains on our tongue. So this all angles are alpha. Okay, all are alpha. Okay, all are alpha. So that becomes 1 plus mu quad alpha and divided by over here cos alpha by sin alpha will be cot of alpha and minus of mu. Now this A max is basically W max because I said that I am taking A as a W. So the overall result becomes W max is equal to G into 1 plus K cot alpha, because the mu is basically K, the friction coefficient is K, and divided by that's cot of alpha minus of K. And do you understand now the condition given here? K is less than cot of alpha. That's a condition given. K is less than cot alpha. So K has to be less than cot alpha. Otherwise, the sign of the acceleration changes and the question altogether becomes meaningless. Now you might think, so just change it. So that means that the acceleration was applied in the opposite direction. So that what? The whole idea will change. The directions of the friction might change. That will be an altogether different analysis. Yes, of course. Yes, of course. This idea is understood that why the K was given less than cot alpha, because that is a clubbed condition. Without that condition, you cannot generate this answer. So if that is not given, you must mention that alongside with the solution that K has to be less than cot alpha for this condition to be valid. And of course, you might get a question, find a value for the minimum acceleration. For the minimum acceleration, you might be tempted to do so, that take minus in the numerator and a plus in the denominator. Reason because the friction is going to act up. The friction is going to act up, and so all the signs are going to change. And you will get something like that. So you can try that particular part to find the value for the minimum acceleration. I have another one for us. And this time, the question is, what is the minimum acceleration with which the bar A should be shifted horizontally? Now, see, I left that minimum question over there for you. So I have this idea that I should be solving one of the minimum question also. So I'm just trying to pace up the kind of the question with the languages. So that was maximum and this is minimum, right? Overall, the idea is same. That's the stationary relative to the frame. And that's been the idea which we have picked up in the today's lecture. The masses of the bodies are equal and friction between the bar and the bodies is equal to K. The masses of the pulleys are negligible. They are ideal, pulleys and the thread. The friction in the pulley is also absent, so they behave ideal. So we need to find the minimum acceleration with which it should be shifted horizontally. So the minimum acceleration, A minimum, has to be calculated. Now, there must be some force applied on it which causes this acceleration. But what's all together, it becomes a non-inertial frame and should be acted upon by the pseudo forces. That should be M into A. They are of identical masses, and M into A like this. A is minimum, right? A is over here as a minimum acceleration. So how do we start solving? What are the concepts? I think there is no change in the concepts. The first one being the FBD. The second being the pseudo. The third being the equilibrium. Because it is in a state of the relative rest once again. They are stationary, the particles are stationary relative to the bar. And the fourth is to justify the direction of the friction. The reason is quite simple, because the question says that find a minimum. In the previous it was asking find a maximum, that's all. So since this pseudo magnitude will be lesser, reason the A is small, minimum. So there will be a lesser tendency of pull, which means this mg force might win. Even if this was not moving, this has a tendency to move down. So now you understand why did we apply the force. So there is a pseudo generated over here which can basically balance this mg if there wasn't any friction. But oh, bad luck, there is a friction also. Getting the point? If this was a frictionless behavior, it is simply m equal to mg. And you can solve it from there, take it from there. But the friction is there. So where is the tendency of the motion? Downward, because ma is lesser. That's a minimum force. So mg is more, or the tendency to slide is rightwards. So that's the direction of tendency to slide. That's the direction of tendency to slide. And because of which we will have the friction opposing that tendency. So where does that particular friction acts? So on this friction acts here. And on this the friction acts here. So let's say that's F1 and that's F2. Because the tendency to slide is downward because the pseudo is lesser. That's it. Everything is stationary. There is a tension force in the string here. There is a tension force in the string here. The tension remains the same because the pulley and the threads are ideal. The pseudo compresses it. So it generates a normal reaction, that is N1 over here. There is a normal reaction N2 over here, which is basically balancing the weight over here. Too many forces. Too many forces. So we try to make the free body separate for the bar 2, and we get Ma here, which causes the compression and hence generates a reaction. So N1 is equal to Ma, which generates this friction, which ultimately balances this weight. That's a sequence of activity. So hence this F1 is equal to mg. But F1 is mu times of the contact force. Correct? And that N1 is supposed to be equal to Ma. And meanwhile, we also have that tension. So that tension is adding to F1, upward, balancing this. So T plus mu N1 becomes mg. And then mu N1. N1 becomes equal to how much? Ma. How much is the pseudo compression? That's equal to the reaction. So that's mu Ma as equal to mg. So the tension from here becomes mg minus mu Ma. That's what we get it from this bar. And on a similar note from the bar 1, from this bar, free body for this. There is a tensile force here. There is the pseudo here. There is a friction F2 here. There is a normal here. And there is an mg here. So too many forces. But the solution isn't that difficult, my friend. From horizontal, we have T as Ma and plus F2. While this N2 is equal to mg. And F2 should be mu times N2. Later on, you can substitute mu by K as the question says. So placing the value for the F2, we have Ma and plus mu into N2, where N2 is mg. So that's mu mg. So that's mu mg, and that's the equation 2. And now you can equate the tensions, for which the question says the masses of the pulley and the thread are negligible. So these tensions are going to remain the same. We know that if the pulley would have been having a mass, then the tensions will not be same. But here they are same. So we have the right to equate. So we equate. So hence Ma plus mu mg is equal to, from there, mg minus of mu ma. So you can bring the A terms together. So that should be m first of all getting cancelled out. That's A plus mu into A is equal to G minus mu into G. So A common, 1 plus mu is equal to G into 1 minus mu. So the value for the A, that becomes G into 1 minus mu upon 1 plus mu. All the signs of making that it is minimum, because numerator has negative and denominator has positive. And so we are very much happy to say A minimum. And if the question would have been A maximum, So directions of frictions will change, and this result for A maximum will turn out to be reverse as 1 plus mu upon 1 minus of mu, because of the change in the directions of the friction. Right now the question is this only, and that's G into 1 minus K and upon 1 plus K is the result. And so altogether we did a bunch of questions, but none of them seem to be out of our reach. So they are good questions with the good concepts, and maybe another question comes which is one notch more ahead of it. Another thing might be there is an extra electric field applied and there is a charge on this particular block. Anything might happen. Or as it is moving and there is a magnetic field applied. So the things can change, or the friction can be variable. So many things can add up. Okay, right now we have solved all the questions on the merit basis. We started with a lesser concept question, then we increase it. And the best part is the first question was looking the most difficult, the sliding scissor. I named it the sliding scissor. It was looking the most difficult one, but it turned out to be a simpler of the lot. And we went on doing much better questions. So we'll be coming back again. I'll be coming back again with such more interesting logics and a set of questionnaires. For now, I'm signing off. Enjoy your learning. Bye.